So one of the easiest way to do this is to draw samples. So let's say we have a computational procedure. So we have a certain solver that we code up in MATLAB, for example. Okay, so you take certain inputs. The inputs can be parameter of the differential equation we are solving. It can be initial condition of the differential equation we are solving, and it gives a certain output. So let's just say the input is x, and the output is y. Okay. Now, in a probabilistic computation, my x is no longer a number that is given. My x is now a random variable. So x is a random variable. Okay, and of course, if you want to completely characterize x as a random variable, you need to give me, okay, what is the probability space, and what is x as a function that maps from the probability space to the set of all numbers. But that is usually not given. That is usually not available. All that is available is the distribution. Right? The known distribution can either be PDF or the CDF of the function, of the random variable. Okay, and the task is usually to compute the output y. Okay, the y, because the x, well, although we don't know what x is as a map from omega to numbers, we know x is some kind of a map, right? And y is a function of x. That means y also maps from the probability space to numbers, right? Y is basically is solver x. It's basically a compound function. Okay, it's a compound because x is a function, and if you compound the function of x with the solver function, you get the random variable y. That is a function maps from random space to numbers. Okay, now we know y is a random variable. What is the distribution of y? So, which means either give me the CDF or the PDF. So how do we do that? Okay, so let me introduce probably the easiest thing to do in this case. The easiest thing to do is to example, compute the probability that y is less than a certain number, let's say a. Okay, so that's basically computing the value of the CDF of y, which is equal to the CDF of y at a. So how do we do that? If we know how to compute that, right, we know how to compute the CDF of really y of any value, and then we can basically also compute the PDF of y. We can also compute the mean of y, the standard deviation of y, etc. Okay, so how do we do that? The most straightforward way is to draw random samples. What I'm gonna do is draw random samples of x. Okay, so for example, I'm going to be drawing x1, x2, etc. to xn. I'm drawing a big N number of samples. And the samples has to be according to the probability distribution of X. To its distribution. So what does that mean? What that means is that I know the probability distribution of X, right? I basically want the portion, okay? So the number of X's, or let me just write it like this. So if I sum over the, what I call the indicator function of xi less than a certain value, let's say b, okay, I goes from 1 to n, divided by n. So this is really the proportion of x's whose value is less than b. That proportion has to go to the CDF of x at b as my big N goes to infinity. Right, so I want to draw random samples of X according to the distribution, which means I want, as I draw more and more samples, the proportion of X's that are less than any value is going to be approaching the cumulative density function of P. And what we want to discuss is how do we do that? How do we draw random samples if we know the cumulative density function? And here we are going to be introducing two different methods, and in both methods I want to use a certain example.